All right, welcome. In this video, I want us to start moving away from the deterministic environments we've been looking at in the last couple of videos into stochastic environments, and we can talk about making decisions in those probabilistic or stochastic environments, and these are commonly called Markov decision processes. Before we get into discussing the AI application and the reinforcement learning, we do need to do a little bit of review of probability theory. There's going to be one concept that's going to be important for us in this video and the next, which is going to be the expected value. So we're going to be talking about the expected value of a state, or we're going to be talking about the expected reward from an action. And these carry a sort of technical definition from probability theory, where we have a definition applied to that. So specifically, we're going to be looking at expected value of discrete random variables, which is sort of the simplest example. A random variable is just going to be some variable that can take on different states, and that variable has probabilities associated with each of those possible states. We usually call them outcomes when we're talking about a probabilistic trial. So an example here might be we have a six-sided die, and it has six possible outcomes, and those outcomes are 1, 2, 3, 4, 5, 6. And then in at least a fair die, each of them is going to have the same probability of 1/6 chance of arising. So if we wanted to calculate the expected value, we can use the formula here, the definition of an expected value, which is summing over all the possible outcomes. We take the outcome itself and we multiply it by the probability of achieving that outcome. So this is a weighted sum of the outcomes weighted by their probability. So let's just take a second and calculate that and see what that does for us. So if we take each of the outcomes and we add them up, they're all weighted by 1/6. So I've moved the 1/6 out front here. So we just get 1 plus 2 plus 3 plus 4 plus 5 plus 6. We take that all and we divide it by 6. We're going to get 3.5. So what is that explaining for us for this particular random variable, the six-sided die? Well, it's telling us the way we like to interpret this is that this is sort of like the cutoff point or the line where we have 50% of the outcomes occurring above this line and we have 50% of the outcomes occurring below this line. So if we actually think about doing that, if we take 3.5 and we think about drawing a line here at where 3.5 would be, it would separate the first three outcomes from the last three outcomes, and it sort of satisfies that definition for us, the idea that there is a 50% chance of being below that line and a 50% chance of being above that line. So that's one way we can interpret that. The other idea is, or the name expected value comes from the idea that this is the value that you should expect. And this interpretation, at least on a six-sided die, is a little bit strange because it says that the value that we should expect to see on the six-sided die is 3.5. That's not a value that's even possible to see on a six-sided die. So that's why it's important for us to take a step back and remember this mathematical definition, meaning that really what the 3.5 is telling us is that half of the outcomes are below and half of the outcomes are above. And 3.5 just happens to be that spot where if we draw that line, it would in fact equally sort of divide out those outcomes for us, at least for this experiment. So again, what we're going to be thinking about in our, going forward in our environment is that we might have a probabilistic distribution related to the reward function or to our transition function. And we're going to use this same kind of idea to calculate the expected value of those functions instead of their exact utility, which is what we were doing in the deterministic case. So to get started and start thinking about probabilistic experiments and stochastic environments, a classic example is called the multi-armed bandit, and it's inspired by slot machines in a casino. So we can imagine ourselves being in a casino and being faced with this sort of problem. I've sort of simplified it and generalized it a little bit here. So imagine there are 5 slot machines in front of you, and most slot machines are not really worth the play because they're designed to make the casino win. But let's imagine for this example that maybe your friend, someone tells you, no, there's a sweet machine in this casino. Its wiring is, backwards or something, and it's good. It helped you win a lot on it, and you should go play it. You want to go make some money, go play this machine. So when you get to the casino, there are 5 machines here, and you're not sure which machine it was. Your friend didn't tell you which one it was. So now you have to figure out which machine which machine has the good payout. That's sort of the thought experiment behind the multi-arm bandit. In a second, we'll have a chance to kind of try and play this a little bit ourselves. So the way that the slot machines work, at least in our example, is pretty straightforward. That each arm, first of all, has a cost to pull. So that's sort of built into the idea, so that you can't just go and pull them all a bunch of times. That, if you could do that, that would be a beneficial way to start learning something about them. But we're going to say that there's some cost associated, let's say $1. And then for each time you play, then you pull the arm, you press the button, whatever it is. In this older example, we imagine pulling a lever, and then there's a probability that you're going to win. And again, that probability is not known to us ahead of time. That's something that we would like to know. Our friend told us one of them is good at winning, whatever that means. Maybe it means it wins a lot. So after you pull the lever, you get a chance of winning, and if you do win, then you're going to get some reward. But your reward isn't necessarily going to be the same every time. Sometimes we consider that in this example, but in my example here, I'm going to assume that there's sort of like a minimum reward for this machine, and there's a maximum reward for this machine. And when you win, we're just going to uniformly pick some value in that range, integers in that range. So maybe our minimum is 5, our maximum is 10. We just randomly pick one of those 6 numbers as our reward when we win. So as I mentioned already, the learning task, or the challenge that is posed to us as human beings, or maybe an AI that was also trying to solve this task, is figure out which arm is the lucky one, assuming we've got our friend who told us there's a lucky one, or just figure out if any of them are worth pulling at all. Are any of them lucky enough or good enough to justify to keep playing them, or are all of them wired so that the casino is going to win? So this is the task, and you can again sit down and think, what would you do in this situation? How would you figure out which is the lucky machine? And while you're doing this, while you're imagining what your strategy might do, you're employing, or you're facing, what is classically called an exploration versus an exploitation trade-off. What that means is that you have a challenge before you where you might want to pull a lever that you think is good. That's exploitation, exploiting the knowledge that you already have in front of you. Or you might see another machine down the aisle that you haven't tried yet that you think that might be, maybe that's the lucky machine. You might want to go and explore. And that's the trade-off. It's very common in learning tasks faced by AI, but also by natural creatures, animals and such, is that you need to know, when should I exploit the knowledge that I have, and when should I go out and seek new knowledge. Maybe my current knowledge is not sufficient to get me where I need to be. So in our little assignment, our little task here with the multi-armed bandit, let's imagine first that what we're trying to do is estimate some of these different values that are maybe related to the machine. So one of them is its chance of paying out, chance of giving us a reward. So again, maybe we imagine a machine is programmed to give out 50% of the time. It rewards us 50% of the time. Then if we tested that machine and we did 4 pulls on it, we might expect that 2 of them will be successes and 2 of them will be failures. Now I say we might expect that because that's the most likely outcome if indeed it has a 50% chance of winning. But of course all the other outcomes are also likely. We could have 4 wins or 4 loses with 50% chance. It's still not really out of this world to have 4 in a row. But what we can see is that we can start to estimate what that probability might be by keeping track of how many rewards there have been and how many times we have tried. And with that number, we can maybe try to guess what that percent chance of winning is in the machine's code or whatever it might be. Now that's sort of our first task, but our second task then is to then try and figure out, well, how much money is coming out of this machine when I do win? So some machines might be programmed to pay out more than others. And again, as I mentioned earlier, we have a sort of a variable amount of payout. So every time we win, it doesn't give us the same amount, or it's not guaranteed to. So we might want to compute, well, what is the average payout? An average payout in this case is equivalent to the expected payout. So given that we win, given that we win, if we want to know what that expected payout is, what we mean is the average payout, okay? And in this case, it's average because I assumed that it was a uniform distribution, so they all have an equal chance. If there was a non-uniform distribution, we could apply the definition of expected value here and use the probabilities as the weights of the different payouts. Because I wanted my example to be a little bit easier, I stuck with a uniform distribution here. So in this case, our average is straightforwardly applied. We're just going to take the number of times we've been rewarded, add up the payouts for those rewards, and just divide by that value. So that's a straightforward application. But now what we're going to see here is we've computed two things. We've computed the chance that we're going to be rewarded, and then we've computed how much we might expect to be rewarded if we got rewarded. Okay, so let's just make up some numbers. So let's say that the average reward that we've seen so far after, however many trials has been $4. And let's assume that the reward chance that we had, let's say we observed like the one that I mentioned earlier, maybe it's 50% chance. So we think we have a 50% chance of winning, and when we do win, we win $4. Then putting those together, since we only win 50% of the time, if we were going to make one attempt, put in $1, what we should expect to win, what the expected value will tell us we should expect to win, is $2, half of 4. Because what it's doing is combining the information together. Let's do that now. When we put this information together, what we're doing is we're taking the chance of the reward plus the value of the reward and incorporating both of those ideas that we've calculated together to compute what the expected reward will be using both of those pieces of information. So on one poll, what should we expect to get out? $2 in that example. Well, that might mean that what it's really trying to say to us is that 50% of the time you're going to pull and lose and you're going to get $0, but 50% of the time you're going to pull and win, and on average you're going to get $4. And so averaging those two out, 50% chance of 4 and 50% chance of 0, will give you $2. That's where we got that number from. Okay, so this is what we're considering to be the expected reward for our arm. So why are we discussing this? Well, what we're describing is learning a probabilistic model. We're describing learning the reward function and what we can expect for the reward function if randomness is now in the picture. So using deterministic calculations, that's what we've done for the last couple videos. Now we can add in probability and still, just by using this definition of expected value, extend the strategies that we've been looking at in deterministic environments to stochastic environments as well. So the last bit of this that really makes this work is one of the axioms or fundamental principles in probability theory is called the law of big numbers. What this tells us is if we keep sampling this reward function or we keep sampling this machine and trying to figure out what its payout percentage is, if we do that enough, as n gets big, as we pull the arm enough, these estimates that we have are going to get closer and closer to the actual value. So after some amount of time, our estimates are going to be very accurate. And now we might be able to use them to make predictions about the machines. We might be able to say this is the lucky machine or this is not the lucky machine. And that's going to be our goal. Now, I've also mentioned that at some point, we are going to face this exploration-exploitation trade-off. And it's not usually just one time, it's usually throughout the time. We're always kind of asking ourselves, should I keep exploring or exploiting, or should I switch to the other option? So in this problem, it's going to be, should I keep pulling this arm, or should I go out and try and see if maybe there's a better arm? The last thing I'm going to do before we try this is I'm going to mention that why this is an important example is this is sometimes considered a very simple example of a probabilistic state machine. So while I haven't used this phrase state machine explicitly in the last couple videos, what we've been talking about are state machines, states that have transitions between them. And these transitions in our examples have been actions that we can take, move north, move east, things like that. That causes a transition between the states. In a probabilistic state machine, when you try and make a transition, your chance of arriving at the new state is not 1. In a deterministic case, you're always guaranteed to arrive at that new destination state, but in a probabilistic state machine, you don't know which state you necessarily are going to end up with. You might have predictions, but again, it's not guaranteed. It's generated by some random choice. So the multi-armed bandit we can sort of think of as being a single state machine, meaning after each action we arrive back at the same state, because there are 5 possible actions that we can carry out here, pulling each of our 5 arms, at least in this 5-armed example. So we might use a state diagram to describe this. There's one state standing in front of the slot machines, and then we can pull each arm. All that's different from pulling each arm is the reward function that determines what reward we're going to get as a result. And so in this example, in this diagram, I haven't shown the reward function. Sometimes we might have the reward function as intermediate states, depending on what kind of state machine you've got. But it's just a very simple introduction to this new idea of a probabilistic state machine. And as we move out into our larger examples, we'll see examples that are more than one state. Okay, so here's my example of my multi-armed bandit simulation. And we can now play it and explore and try and see, how this strategy of computing the expected reward might help us determine which arm is the lucky one. So I'm going to start with the first arm here, and I'm going to play it. And it looks like we've won. So we won $1. So taking a look at this machine, again, computing these values now since we've only made one pull and we've won, we had 100% chance as our prediction. We think this arm is always a winner. Okay, now maybe we can probably already imagine that's maybe not enough information. We don't know if this one's a winner yet. Now the other thing we've seen is that our payout is $1. So at the very least, faced with the exploitation trade-off, right away I might think I want to do this one again. But maybe let's explore a little bit. Let's see if anyone else comes up as 100%. So I'm going to try arm number 2. Okay, I lost. So that one is 0%. Again, our predictions are really extreme here. We think the first one is really awesome. We think this one's really bad. Let's try the third one. Okay, I win. And it's $6. We got $6 out. So sorry, arm number 1, you're not sort of the winner anymore, because let's take a look at how this calculation works. So here we had a 100% chance of winning $1, so our expected reward is $1. Over here we have a 100% chance of winning $6, so I have $6, and so multiplying those together gives us a $6 expected value. So if we want to exploit, usually what we want to do is pick the one with the highest expected reward, because that's the one that we expect is going to give us the most. Okay, now again, arm number 2 has expected reward of 0. That's pretty terrible. The only thing it's got going for it is we've only made one try on it. So maybe we haven't explored it enough. So let's keep going. I want to maybe get one pull on each of the arms. Again, if you think we want to build the cost in here to help us think that, hey, there is a cost associated with playing this game. So we can't just go out and click them all a million times. We want to carefully spend the resources that we have so that we don't, exhaust them and run out. We want to win money eventually. So let's try number 4. We'll do one. Ooh, another 0. That one didn't come in with a win. Let's try arm number 5. Also loss. So now we spent $5, but we ended up winning 7. So far so good. Thank you, arm number 3. Okay, now we're really at the exploration trade-off. We can decide to keep exploiting arm 3, and honestly that's what I kind of want. I want more of that sweet $6 action. But we could also say some of these other ones maybe are worth another check. So I am going to just try arm 3 for a bit here. Let's try. Okay, so the second pull here was a loss, which is maybe expected. We really shouldn't expect these machines to be paying out 100%. Maybe there are some, but this one confirmed for us that this one at least is not paying out 100%. Okay, and so notice how it's changed our expected reward. We now have 50% chance times our $6 payout. We only had one payout so far, and it was $6. So our expected reward is now $3. We've halved it. So again, it's still our leader. It's still our best one. So I'm going to try it again. Oh, another loss. We're down to 33% now, where our expected reward is down to 2. Okay, let's try. I'm going to keep trying. It's still the best one. And if we keep this for a long time, it might always be. Maybe we found the lucky one. Let's keep trying. Okay, it's not looking as lucky. Maybe now I'm starting to think that we got lucky the first time around. We got lucky and got a reward, and now we're just starting to see the actual performance of this arm. I kind of want to try one more time. Okay, it's starting to, we can keep going here. Okay, let's try one more. Oh, gee, now we're down to 1. We're all the way down to 1, and this one is at 1 as well. At the moment, it's a tie. Maybe out of loyalty, I'm going to give you one more try, arm 3. Ooh, it's hurting me now. Okay, so we got lucky on the first one. We're down to a 14% chance win rate is that's what our actual win rate is. That's how much we've won. And we're using our actual win rate to predict what we think the win rate of this arm is. So now you see our expected reward has dipped down below 0.8. So part of me is like, we haven't explored arm 2, 4, or 5 yet. We have once, and they came up 0, so we think they're kind of bad. But after my experience with arm 3 here, I'm starting to think, okay, that one burnt me. Maybe it's worthwhile to go explore these other ones. Maybe we only got unlucky on some of those ones, just like we got lucky on this one. Also notice total cost is 11. We're not in the winning right now. We're in the losing. So I'm going to go back to arm 1 and try it again, because at least it's my highest right now. I'm basically stuck in an exploit loop right now. We explored each one of them one time, and then we exploited. We exploited arm 3 until it wasn't the best one anymore, and now we're exploiting arm 1. So I did it again, and I actually won. We got another $1. So let's try another one. I'm trying it because it's my winner right now. I'm stuck in an exploit loop. I have not yet decided to go back to explore. Another win and another $1. Another win and another $1. Now, this is looking a little suspicious to me, and I'm happy that I keep winning. This 100% is really making me happy, but I haven't ever won, and I keep winning, and I keep only getting $1. And it's kind of safe for me to do this, so maybe I'll keep trying. As long as that's happening, I'm not really losing money to do that, but I haven't gained any. I'm still $4 in the hole. That's where I was to start out. So one thing I'm coming to a conclusion about this one here, this arm, is that it seems to pay out every time. So it's maybe broken, but it only gives me back the $1 that I put in. It's like I put the $1 in and it just spits it back out. So is it worth pulling? It's not losing me money, but it's not gaining me anything, so doesn't seem to be worth pulling. So I'm going to write this arm off. Sorry, arm 1, you're not awful, but you're not good enough. What does that leave us with? If we go back to our exploit loop, this one's even worse off. So arm 3 is not any better. It doesn't look like. It's certainly not better. So now it brings me into the space. I think I want to go back out to explore some more. And what should I explore? Well, there are different exploration strategies that we might follow. And this case, a very common one is, well, look for places that you haven't explored very much yet. So these ones are the ones that only have 1 pull. So I'm going to go to arm 2 now and try again. Okay, another loss. All right, well, I'm willing to invest a little bit of money in this exploration. So I'm going to try it again. Okay, I got a win. We got $1. And because I lost some, this is not looking good, but I'm willing to try again. Okay, another loss. So not looking great. Percent-wise, not great, and my payout hasn't been very good. And again, another loss. Okay, so this one's really looking bad to me. Remember, we've written this one off not because it's got a bad expected reward necessarily. It's not worse than these other two, but just because it's not good enough. It's not above 1. But these two, I'm starting to write them off. We've only done 5 tries and 7 tries. Remember, it's easy to get unlucky if you've only done 5. But I'm still trying to find the lucky one. My friend said there's a lucky one, so I want to find a lucky one. So I'm going to try arm 4. Another loss. Another loss. Another loss. And another loss. So this one looks really unlucky to me. I don't even know if I want to invest any more money into this one. It's still at 0% after 5. But okay, what does that mean? Maybe it's got less than a 20% payout. So I guess we haven't really explored that much. Okay, but it's enough for me. You know, I moved away after 5 on this, so I'm going to try this one. I'm try arm 5 now. Another loss, loss, loss. Okay, these two are kind of, they seem to be losing a lot. But there's something here that's making me, you know, still curious and wanting to explore them, which is we haven't won once. At least over here we did win, and we only won $1, so it made it seem like this one's not very good. But at this point, none of the arms are looking good. So it's either walk away, and that's sometimes the right answer at the slot machine, usually. The other time is, well, maybe explore some more. So again, remember, our friend promised there's a lucky one. We haven't found it yet. Let's keep going. My best guess is maybe it's 2 or 3. These two haven't paid out, so I don't know. So I'm going to try 2 some more. All right, we won. And we got 3 points. So over here we were getting $1. Here we're getting $3. So this one is starting to look better. It boosted our expected reward. It's still not better than 1, but it boosted it. Now I'm starting to think to myself, maybe I want to really get a more accurate look at this arm. So I'm going to try another couple. I won 1 point. Okay. I lost. Lost again. I won 1 point. Okay. My expected reward still hasn't gone up to, you know, a point where I really want it, but that exploration helped me see a little bit better what that payout is. I'm going to go back to these two. I still haven't found the lucky one. I'm looking for the lucky one. 6, 7. I'm going to invest 5 more pulls in these ones, I've decided. Oh, geez. Number 4, you seem very unlucky. Okay, now I've done 10 pulls and not won once. So that seems like less than 10% chance. Okay, let's do arm number 5, see how we do here. 7, 8. Hey, we finally got a 1. Okay, wait a second. I won 97 points. I won $97. I like this one already. My expected reward is 11.6, even though I've only won 12% of the time. Okay, this is a great way to show how just because something isn't paying out very much, like maybe arm number 4, if it pays out a high amount when it does, it could be really awesome. It could be our best one. So now I'm greedy. So I've explored, and now I found arm 5, and arm 5 looks awesome. Maybe this is the lucky one. I'm going to try it again. Okay, we got a loss. And another loss. Well, it's not paying out very much. It's at 10% now. Notice as I keep getting losses, my expected reward goes down, but it has to go down to 1 before it gets worse than any of our other ones. So I'm happy to keep exploiting this one for a while. Okay. Again, look, if you're at the casino, you might be feeling a little euphoria right now. You've only spent $47 here, and you're up to 119. So I've got some winning that I can spend on this one. I'm going to pull this arm a little bit. By the way, none of this is gambling advice. Please do not take this as advice on how to gamble. So I'm going to pull this one here. Again, losing. See, this is why it's not a good gambling advice, because now I'm really invested in this one. I think it's awesome. And I'm going to keep pulling it until it pays me out again. So now I've done 20 pulls, and I've only won once. So I'm now estimating it's got a 5% chance of winning. But when I won, it won so good. So let's keep trying. I really want to get a better... Oh my God, that reward chance is just dropping. But my expected reward is... If I'm just playing the numbers game, it's still telling me to pull this one. Woohoo! We get another win. What was this one? 90 points. It boosted us back up again. It really makes me want to keep playing this one. So I am. I'm going to keep exploiting. Oh, 99 points. This one seems really good. Okay. How good? I'm really sticking with this one. But maybe we got lucky, because we got 2 kind of wins in a row there. And remember, it's only paying out about 6% of the time. 5% of the time. I'm going to go all the way to 100 with this one. I really like this one. I'm up to $300. I'm going to spend the whole night gambling this one. I won 43 points. That's the smallest I've won on this one. But my average reward is still really high, and my expected payout is still doing good. Keep going. Okay, okay. Now it's maybe making me pay, saying, look, you, ooh, we got one more win. We're going to go up to 100 and see where I end. Okay. So playing this one 100 times, we managed to get about a reward chance of 5%. Now, the law of big numbers is telling us that this is probably getting pretty close. If we only won 5 out of 100 times, it's probably about 5%. Maybe it's 6, maybe it's 4, maybe it's 10, maybe it's 2, I don't know. But it's probably getting pretty close to that. Our average reward, well, we've only got 5 rewards, so this is probably not very accurate. But it's still telling us this is a pretty lucky arm, okay? If you're like me, I'm now suspicious about arm 4. Arm 5 turned out to be really good. Arm 4 is still paying me 0. I think I'm willing. I've now got enough winnings here. I'm going to go and invest some into arm 4. Let's try arm 4 a bit. Please give us a win here, arm 4. Okay, we got a win, 15. It's at about 4% chance we got 15. It's because we invested so much in it, it doesn't seem like it's very good. 15 certainly wasn't as high as some of those ones over there, but I'm still willing to try it a bit more. Another 15. Another 15. I'm seeing a pattern here. Another 15. Okay, I only did 15 pulls on this one now, but let's pause and see where we're at. This one seems to be paying out about 8%, and it pays out 15. I'm pretty confident in that one. I got 15 every time. 4 times I've only been rewarded, but I got rewarded 15 every time, giving me an expected reward of 1.2. So this one seems lucky enough to me to play, because at 1.2 I'm still making money. These other ones not so much. But again, let's go back and explore a little bit more. Number 1, okay, let's just make sure. Is it still 100%? This one looks like we figured that one out. So let's pull number 2. I'm just going to go up to 20 again. And not doing much. It's about 45% now. Okay, average reward 1.8, meaning that we're just a little bit under 1, so not really worth pulling. So up to 10. We've now been rewarded 3 times with this one. Average reward of 11.3. We're doing good. This one's actually pretty good with a couple wins, even though we got some losses there. We got 2 wins in a row, and that's boosted us back up. So let's keep playing this one a little bit. Okay, we're losing again. Losing, it's going down. Another win. Okay, sort of going back and forth as we win and lose. We go up and down as we win and lose. We're up to 9 rewards now. I'm going to go up to 50 as well. Okay, 10 rewards on that last one. We got a 20% chance with an average of 9.6. Okay, so at this point, now maybe we could say it's time for double or nothing, or all or nothing. If you had to pick which of these machines did you think your friend said was the lucky machine, are you confident enough? Do you want to explore some more? Or are you ready now to just give up on the exploration and exploit? And if so, which one would you vote for? I personally am liking arm number 5. Arm number 5 is looking like the one I would like to pull. But some of these other arms are not looking super bad. Arm number 3 doesn't necessarily look bad. Its expected reward is 1.9. And arm number 4, I'm not sure I'm convinced that we've got all our numbers right here. I think the 15 was right, but our 8%, maybe it's higher or lower than that. If it's lower than that, this might not be worth it. If it's higher than that, it is going to be worth it. Well, how are we ever going to know? The only way we're going to know if we are faced with this black box is to keep pulling the arms and pull them until they're at 1 million. If they're at 1 million, the law of big numbers says that these predictions will be really, really close, and our confidence levels will go up. But the other way we can do it is we can just look at the code. So if it's a website like this, we can go take a look. So here are the actual probabilities and reward ranges for this example. So it looks like the first one was indeed paying out 100% of the time, and it was also paying out $1 every time, so by design. The second one was paying out 50% of the time. We had an estimate of 45% of the time, and its average is 2. So its expected payout, 50% times 2, is 1. So both of these first arms don't win any money, but they also don't lose any money. They're not good for the casino, and they're not good for us either. The next one, let's look at its payout was 20%. I think that's what our prediction was. And it was going between 5 and 15. So its average was 10. Let's take a look at what we had for that. We have an average reward of about 9.6, and we had exactly got 20%. So with these two, we had only pulled 20 times. Now, this first one's deterministic. It's not even random, so it only took us one time to figure it out. But the next one was probabilistic, and look, we're off. The actual value was 50%. The actual value here is 2. The actual value for the expected reward is 1. But for this one, our actual reward chance is 20%. We're actually getting pretty accurate. The actual reward, average reward I should say, is 10 here, $10 I guess, and after 50 pulls we're getting pretty close to that at 9.6. And our expected reward here is 2, but our prediction is pretty close. So we're actually pretty good with that. So let's look at the next one. The next one is actually paying out 10% with 15. We figured that part out. We figured out that it was making 15, but it's 10% of the time. So what does that mean its expected reward is? Well, again, 10% times 15 is going to be 1.5. Again, let's double check and see what we had. We had our average reward is 15. That was accurate. But our reward chance was only 8%, so our expected reward here was 1.2. So not quite. Remember I said if it was bigger, it would be better. If it's less, then it would be worse. So in this case, we actually were off. The actual reward chance was 10%. And then the last one here, well, that was the one that we thought was the winner. Its payout probability is 5%, or 1 in 20 chance. That's very low, but that's why we got so many failures at the beginning. Okay, but once it pays out between 1 and 100. Okay, wait a second. The average pay, or the actual min and max here was 1 in 100. The payouts that we got for this were like 97, 94, 99, 51. We got a bunch of really high payouts. The average reward we got here is 76, but the actual average reward was 50. Or 50.5 technically. The actual average was way less. So because we only got 5 rewards, this prediction is way off. But 5 rewards out of 100 was exactly how many we would have expected in this case. So we probably need more exploration on ARM 5 to figure out what its actual payout's going to be. Okay, and we can probably now compute that ourselves. All we need to do is figure out what is the average payout here, or the expected payout in this range. I mentioned it's 50, technically it's 50 and a half. And if we take that 50 and a half and we multiply it by 5%, what do we get? We get 2.5. So the payout of this last one is actually 2.5 when our current prediction is at 3.8. So it turns out ARM 5 actually is the lucky one in the sense that it's the one that is the luckiest. But the payout of ARM 3 was 2, and the payout of ARM 4 was 1.5, so they're both also lucky. And the first two payouts were payout 1, or expected reward of 1, meaning that this is a bad casino. This casino is losing money, or this is not set up properly. Okay, so that's the one thing we learned at least from this setup. But now we've just explored what it's like to do that multi-arm bandit problem. And so we've got our first experience of what it's like to do decision making in a probabilistic state machine. So we have been looking at state machines so far. We have states and we have transitions, actions that move us from one state to another. In the probabilistic world, we've got the same thing, except now we express it like this, not a function that moves us. Before we had delta, the transition function, now we have p, a probability estimate. It's going to tell us the probability of ending up in state S prime, given, that's what the vertical bar there means, given that we were in state S taking action A. So if we're given state S, we take action A, we might end up in state S prime, and this expresses the probability that we might end up in S prime. And I say we might because that probability might be 1, meaning we always end up in S prime. It could be 0, meaning we never end up in S prime, or it could be something in between, meaning we have a chance of ending up in state S prime. The thing that the probabilistic state machine brings in is that for any state with any given action, we now have the potential for ending up in different states. We might not always end up in the same deterministic state. Now, if you're familiar with probability theory, to make sure all of our probability math works out, it's important that probabilities add up to 1. So in state S, if we're taking action A, all of the possible states that we add up to, if we sum over all of their probabilities, it should add up to 1. And that's something we're going to see. Now let's take a look at an example probabilistic world coming from the perspective of our reinforcement learning agent. Our simple world that we have will still work, but now what I'm going to do is add some uncertainty to the outcomes of our actions. So say we're this little robot here and we want to move north or up to the cell above us, then we're going to take an action called move up or move north or whatever it might be in our code. Now in the deterministic world, we are guaranteed with probability 1 that we arrive at the state that we were intending to arrive at. In the probabilistic world, at least in this case, I'm going to say, imagine we have icy floors, so it's slippery. So by accident, when the robot moves, it might not end up in the state at once, it might end up in one of the states to its left or its right. So it's moving forward, it might slip to the left or it might slip to the right. I've got sort of transparency here to kind of indicate the probabilistic chance. So here in my model, at least the default numbers, are that we will end up with an 80% chance of following the direction we want, and then we'll have a 10% chance of slipping to either of the left or the right. So 10 to the left, 10 to the right, adding up to 100 total. Okay, so this is just what I'm going to build into my environment to now make it a probabilistic environment. And since it's a probabilistic environment, we need to reason about things differently. Let's see how adding probability to our state machine or to our environment now impacts the updates that we might do. So we've been looking at a way of updating the value function is what we called, or computing the utility. What we were looking at in our deterministic version. So this is the deterministic update that we were looking at. Okay, this is due to a gentleman named Richard Bellman who studied this in the 50s. And he was the first to propose this recursive definition for what is now known as the Bellman equation or the Bellman update. This expression brings in probability where before we had determinism. So before the probability was 1. So if we took an action from state S, an action A, we would use the transition function delta to tell us what the new state would be. And we would just look what that state is and find its utility. So in the old update, we would try and maximize by finding the maximum state we could move to given the actions. Well, in the new equation, we're going to do the same thing, except we're going to substitute in here for the resultant state. Instead of there only being one state that happens with probability 1, we're going to substitute in the expected value of that outcome. So what state would we expect to get into? So we will sum over the utilities of all the possible states we might arrive at, and we'll weight each one of those by the probability that we would arrive in that state. So this is taking, so let's imagine our slippy environment now. This would say the state we want to move in we'll have an 80% chance of moving to it, so we'll take its utility and multiply it by 80%. And then the other two states that we might accidentally arrive in, we'll go figure out what their utilities are, and we'll multiply them by 10% so they contribute less to this sum because it's a weighted sum. And then that will express the expected utility of taking this action A. So what that means is when we take that action A, we don't know what state we're going to arrive at, but we can still predict what the utility would be of making that action based on the possible states we might arrive in. What else are we looking at in this equation that, we've looked at this before, but I want to bring it back in again. What is this gamma here? The gamma is our discount factor. Remember, we want to value current or present rewards more than we want to value rewards that were distant in the past or distant in the future. So to do that, we're going to use this gamma. So this is saying in our next state, since that's in the future, we're going to apply one copy of our discount factor to that calculation. And then the other thing that's contributing here is just RS. That's just the reward we received when we hit this state. Okay, the reward that we received. Now, what we're going to see here is in these two equations, we see the reward function showing up. In the original version, we also saw the transition function delta showing up. That was the model. That's what we called the model of the environment, the reward function and the transition function. And we, in our deterministic world, if we know the model, then we can compute the value function, we can compute the utilities. And if we can compute the utilities, we can come up with a policy, a strategy for carrying out actions in that environment. So the same thing is going to be true in the stochastic environment, which is we can take the model, which is the reward, but now our model is not just the deterministic transition function. It's now this probabilistic transition function. So we need to know the probabilities of each of our transitions to be able to apply this rule. Keep in mind what we've just been doing for the last little bit is figuring out ways to estimate these probabilities if we don't know what they are. So if you don't know what the actual probabilities of your transition probabilities are, you can still use this update using your estimates. And that's the idea that we're going to get to in applying this update in our reinforcement agents. So same thing with the reward function. We were just computing in our last example, we were estimating what that reward was going to be, the average reward. We can stand in with that estimate here instead of the actual one. However, if we do know the actual reward function and we do know the actual probabilities, then we can compute this exactly using the actual values. So one thing I do want to do, you'll notice the only change that I've made in these two equations is I've changed u to v. What's up with that? So this is actually just a subtle difference in how we sometimes express these. That up here what we're doing is we actually have a definition for what utility is. This is a recursive definition for what utility of a state is. That's a mathematical object. It can exist out there. We don't need to do anything with it. We can talk about it, prove theorems about it, but it doesn't actually exist in our code anywhere. Instead, in our code, we're going to have something called the value of the state, which is our current estimate of the utility of the state. But it's not equal to the utility of the state because we haven't actually computed it yet. And in some cases, we might never be able to accurately compute the actual utility of the state. Instead, we're computing this stand-in. This is what the agent might have represented in its model that it's using to represent the utility, but again, it's just an approximation of it. For that reason, we give them different names. This is u, the thing we're trying to compute. This is v, the tool that we are using to compute it. With that said, these two equations are exactly the same. This is the one that defines recursively the utility. This is how we compute the utility from its states, the resultant states from any particular action. So we can apply this in an algorithm that will compute the utility of the states in our environment. And we saw a couple examples of that in our previous videos. I'm going to show you an example here in a second, but I want to talk a little bit about how we might employ this in our own model. So first of all, every time we apply a new action, especially if we're exploring and we don't know the model ahead of time, we will hopefully learn something new about the model. We'll do another sample of a probabilistic distribution, or we'll maybe take a new action we've never taken before. That's going to add information into that model, meaning we can recompute our utilities and we can recompute our value function. When we do that, what do we want to do? Well, the most common thing to do, if you have the whole model, is to compute the whole value function, compute it for all the states. Or if you don't have a fully observed world, maybe compute it for all the observed states, all the ones that you've currently had a chance to exist in. Other common things, maybe the number of observed states you have is very numerous and it's expensive for you to update all of them every time you take an action. Then it's common to maybe only update recent states. Why recent states? Well, those are the states that are most likely going to be changed by the new information, those stuff that you're getting right now in your current exploration. So since they're the most likely ones to be updated, those are the ones maybe we should prioritize when we're selecting some over others to update. In the most stingy of update schedules, you would only update the current state. And that's if, that's actually in the value iteration update schedule, that's very rare. Okay, I can't really think of a good reason why you might do that instead of updating a batch of recent states larger than just a single one, but that's taking that to its extreme. However, it's starting to foreshadow a little bit Q-learning, which will be something that we talk about in our next video, where we can only update the current state as a result of our new information, and so that's something that we are kind of forced to do, so we're foreshadowing that. Okay, so let's come back to an example of doing value iteration now in a stochastic environment. So stochastic meaning probabilistic. You can see I now have my icy flag on, and you can see that the background is a little bit bluer. That's to indicate that we've got the slippiness now built into the model. So when we move forward, we have a chance of slipping to the left or to the right. As a result, we can still calculate our value function. So I'm going to compute the value function. Maybe it's been a second since you watched that last video, so let's do a quick let's go back, and we'll go back to the non-icy version and we'll compute the value function. Notice in this value function, our starting square has a value of 48. This is again the deterministic world. So let's switch it back to the icy world and compute the value function. We now see our starting value has actually got value 9. Okay, and there's a different decay in the values as we go around. The reason is because we're no longer guaranteed to arrive at the location that we were expecting. Let's just look at this first cell here. Okay, the first cell before, we had a 100% chance if we move to the right to go to the gold and get the 100. And so as a result, our calculation, let's go back and take a look at it, is 85. Why? How do we get to that math? We take the 100, we multiply it by our discount rate here, which is 0.9, so we're at 90. And then we minus off the 5, the reward that we get in this square, so we get to 85. If we go back to our icy environment, and we compute we now have a 78. Why is that? Well, we now only have an 80% chance of arriving there. Okay. We also have a 10% chance of hitting this wall at the top and bouncing back to right where we are again. And we use this utility to compute what that value is. And then we also have a 10% chance of sliding into this square down below that has a utility of 46. So when we compute that, 80% of 100, 10% of 78, and 10% of 46, and we apply our discount factor to that, we end up with 78, or at least that's how we got here. This is a point of stability, meaning we've applied the value function over and over again, and it's not changing anymore. Okay. Now what we'll notice here, we can again follow our optimal policy by going to the square that has the highest expected utility. Now we're talking about expected utility. We're not talking about the actual utility, but how much we would expect if we try and move in that direction. You'll notice nothing's really changed in our pattern or our plan. If we want to get to the gold, our optimal policy tells us try and go the quickest way there. Notice it's even telling us to walk past the pit that we have a chance of sliding into if we do that. So this is actually a drawback of the value iteration algorithm because it evaluates the values of states and not state action pairs. It is having a hard time recognizing that it should take the long way around here. If you really want to get the utility. You probably should not risk falling in the pit, and you should take the long way around. And other models, other reinforcement learning models might overcome that particular problem. Okay, let's look at another example. This is the ice bridge that I kind of created for this example, which is that we have now a bunch of pits that we obviously don't want to fall into, but we want to cross over this icy bridge to get to the pots of gold at the end. Now you might think for a second, what would be your strategy across this bridge if you have a chance of slipping to the left or the right? Well, you probably would want to avoid the cells on the outside of the bridge. And so let's go ahead and compute our value function. Now when I click this button, compute value function, what it's doing is applying the value iteration algorithm. It's applying one iteration over and over again until all of the states settle down. So it does that really quickly, and you can see how quickly it does it for a small number of states, which is why when we use value iteration, we usually update all the states all the time if we can. If we have a nice small finite number of states, we update them all the time, so we always have a very accurate prediction of our utilities, or in this case, expected utilities. Let's turn our solution back on and see what it's telling us to do. What I was hoping or expecting or wishing it might do is for all of these ones along the edge here, I was hoping it maybe said, no, if you slip and you accidentally end up in one of these squares, you should move towards the middle of the environment because that's where it's safe. Don't keep moving down like this. The more you move down, the more you risk falling into that pit, right? So even if, say, you're moving down the center and you slip over to the right, I would expect the optimal thing would be to move to the left. Well, let's take a look at this square and just see what it's telling us to do. In this square, we're looking to the cells next to us and we're computing what their utility is going to be, right? So when we're looking down here and we're saying we should go to this cell, we're seeing that this cell's utility is 4,337, and since it's bigger than 4,270 and bigger than 3,245 and certainly bigger than minus 10,000, that's the optimal policy for us. But that prediction is only looking at that state as though we could reach that state with certainty. So it's assuming, it's not taking into calculation when it's computing this utility that we might slip, even though it's computed the 10% chance, it's added the 10% of the minus 10,000 on there to compute this value. It's not enough to overrule the other, or not overrule, I should say. The 4,337 is still bigger than the 4,270, and that's why the policy is telling us to move down here. Okay, now in foreshadowing a little bit to Q-learning is going to be able to pick up on this and say, yeah, the action that would take me down has a chance of throwing me in this pit, and because throwing in a pit is really bad, I'm not going to risk taking that action, even though it has a much higher chance of arriving me where I want to go. Okay. Now we might ask ourselves, well, why is this one evaluated higher than this one over here? What is it about this one that makes it better? Well, it's closer to the pot of gold. So in the value iteration algorithm, it actually thinks it's better. Okay. And we might try some variability here to try and change it. Now, one thing I don't have built into this example is changing what the penalty is for each one of these squares. I might reduce that penalty. I might because right now it's at -5. If I reduce it to 0, is that enough to change it? I don't know, because I haven't actually tried that. Okay, you could try that if you want in your own model, or steal my code here, download it, change the value, and see what happens. Okay. The other thing that I've tried doing here is I've tried changing my slippy percent. So what is the slippy percent? 10%. That's how much chance I have of going to the left or the right. So I can actually change this to a kind of ridiculous value, which is 50. I'm going to make a new ice bridge. At 50% chance, what's that saying is if I move forward, I actually have a 0% chance of moving forward. I have a 50% chance of sliding to the left and a 50% chance of sliding to the right. So this is terrible. You never want to move forward. If you want to actually move forward, you should try and move to the left or right and hope you slip in the right direction. Now you can imagine walking down this path would be really bad. Let's see what happens with value iteration. Value iteration, notice how much lower our scores are. Okay, because the chance of sliding into these minus 10,000s got way higher. But it's still telling us to walk straight down. So even with this change, it's impossible for it to identify that even though it's impossible to move down when I want to move down, it's still suggesting to move down. Because why? It's pointing to the state that is the best. That's all it's doing. It's not considering the actions that get us to that state necessarily. So this can be a drawback of value iteration, and one of the reasons why other algorithms like Q-learning are advantageous. All right, I think that's a really good point to maybe transition. In the next video, I am going to be talking about Q-learning. We can take an example of looking at that. Thanks a lot for watching this video about doing Markov decision processes in stochastic environments, and we'll see you again in that next video.